Hi everyone, Dave here. We're now going to start looking at acids and bases. This first mini lecture is just simply titled What is an acid and a base? Okay, before we look at the definition of acids and bases, I just want you to have a thought about what's so unique about hydrogen, because obviously hydrogen's tied up with this whole idea of acids and bases. Just to refresh your memories, you already know this, of course. Hydrogen has one electron. It normally wants to pick up one electron, and in doing so then attains a stable electron configuration like that of the noble gas helium. And I've been repeating that again and again throughout these lectures and tutorials. However, hydrogen, as I think I've pretty much indicated to you already, is also a little unusual. And the reason for that is it can also lose one electron. And this resulting ion that's produced when it loses one electron is also quite stable. So hydrogen's a very odd element indeed, in that in one sense it would like to lose one electron, that is, and also it in some instances will pick up one electron. Now, we've done picking up the electron and looking like helium to death. What happens when it actually loses an electron? Well, first of all, of course, if it loses an electron, it becomes H+. But the important point here is that that ion then is really just a naked proton. Now you might think, well, who cares? Well, of course, protons are exceedingly small in comparison to the size of a normal atom or ion, which has got electrons around the outside of it. In other words, whilst a proton will only have a 1+ charge, the charge itself is extremely concentrated. So in other words, there's a lot of charge for a very, very small volume. And I've written this point here to press home this idea. So a proton has a radius of about 10 to the minus 15 of a meter, and yet the approximate radius of other ions is about 10 to the minus 10 of a meter. You might think, well, that's not much of a difference, 10 and 15, but this is, and you might think, well, the difference here is 5, but it's not 5, of course, it's 10 multiplied by itself 5 times. In other words, a proton is actually 100,000 times smaller than any other ion. So my point here is that it then becomes a region of very high positive concentration of charge. So now I'm going to get on to the definition of an acid and a base, and it's actually quite simple. The definition is this: an acid is a substance that has a tendency to donate a proton, and a base is a substance that has a tendency to accept a proton. And you'll notice up there I've called it the Lowry and Bernstein definition. The reason for this is that there is one other important definition of an acid and base, and that's the Lewis definition, but we're not going to look at that in this course. So there you have it. It's actually quite a simple definition. And of course, sometimes you want to describe what's actually happening in this situation where protons are being given up and accepted by things, that is, by acids and bases. One way in which you can do it is this one here. This is probably not really my preferred option, generally. So I can write my acid here. In this case, it's hydrochloric acid, HCl. And what I'm saying here is it's giving up a proton, there it is there, or a hydrogen ion, or a H+ ion, however you wish to describe it, and of course a chloride ion. And of course it has to be like that, a chloride ion, because overall the components on this side of the equation must be neutral, because we started off here with something neutral. In other words, that electron that's given up by the hydrogen's gone to the chlorine, and there it is as chloride ion. Now, as I said, this isn't my preferred option. this is my preferred option here. So here's our acid again. That's no different to before. What have you done to my pen, you horrible machine? So there's our acid again, no different to before. But of course, if something gives something up, it kind of is implied that something's accepting it. And of course, that thing that's accepting that proton is a base. So what's the base? Well, if you're not told what the base is explicitly, you assume it's actually water, because all of these reactions are occurring in water. So there's my water, and of course this is the acid. It's going to give up a proton. It'll give up a proton to this water molecule, and of course the resulting compound or molecule is going to be this thing. It's going to be H3 because it's given up a H to this water molecule, and of course it's going to be 1 plus because there was 1 plus moved with that H plus there. So we've got this thing here. This thing here is called a hydronium ion, and of course, as before, the other thing that results from all this is a chloride ion, because that electron has ended up with chlorine. The other thing that people like to do is sometimes write in brackets AQ. AQ just stands for aqueous, which means the reaction's happening in water. Actually, technically, I should probably have written an AQ next to that HCl as well. But you get the idea. So that's the preferred option. Now, there is one slightly better way to portray what's going on with acids and bases, and it's this one here. It's not that much different to the previous example I gave you. Here's my HCl. Here's my acid. Here's my base, the water. It gives up a proton, and of course it forms hydronium ion here as before, and chloride ion here as before. However, it's important to realize that the reactions here with these acids and bases actually go in both directions. So not only does it go from left to right, it goes from right to left. Now, normally, of course, we're reading from left to right, but if you're reading from right to left, I hope you can see here that this molecule, the hydronium ion, is actually giving up a proton to that chloride ion, and of course that forms HCl. And of course, as it gives up its H plus ion, it becomes water. So that Lowry and Bernstein definition still holds. This is the acid giving up its proton to this base, which is accepting this proton. So reading from left to right, that's the acid and that's the base. Reading from right to left, that's the acid and that's the base. Which way is it actually going? Well, as I said before, it's going both ways, but what I haven't said is it more favoured over on this side or on this side? It doesn't have to be equal amounts of both, as long as they're just doing this, reacting backwards and forwards. Well, in this case, I know it's favoured more in this direction. In other words, there's a lot of this stuff produced and not very much of this stuff. But it actually depends on the strengths of the acids and bases, and I'll talk about that a little bit more in another mini lecture. Alright, here's an example for you. Here's a question. Explain why this particular acid, this one's nitric acid, HNO3, why it would be considered an acid. Well, of course, it must be giving up a proton, and therefore you could explain that by writing an equation. Here's one of the equations you could use. Here's my I've lost my pen again. Here's my HNO3. We haven't stated what the base is, so because of that you assume it's water. So here's my acid, here's my base. Of course it's giving up a proton to the water forming hydronium ion. What's left over is nitrate ion here, and of course in this case I put my little aqueous signs there as well. The other way to do it, of course, is not to put the water in and do it like I showed you with the first example with HCl, and I guess that would be okay as well, but again this would be this particular equation here would be my first option in terms of how to explain and answer that particular question. Okay, just finally, I just want to quickly run through some of the properties of acids and bases. You kind of know this anyway from everyday experience, or at least partly. Acids taste sour. An example of an acid would be citric acid that's in lemons. Clearly that tastes sour. Another one would be acetic acid, which is present in vinegar. That's got a sour taste as well. They're corrosive to metals. They turn litmus red. Now, I'll just quickly explain what this means. Litmus is an indicator molecule, and there's quite a few of them that are indicator molecules, and they indicate whether an acid is present or a base, usually by changing colour. In this case, when litmus is around in the presence of an acid, it goes a red colour. And there's other indicators, as I said, and they'll change different colours depending on what particular what's present, either the acid or the base. Acids become less acidic when mixed with bases. I think you could probably appreciate that as acids are mixed with bases, those protons are lost, and I'll talk about that a little bit more in a moment. I'll just say here, or in the next mini lecture, or one of them at least, but over here we've got a similar sort of thing going on with bases. As you add acids and bases together, they effectively cancel each other out. The process is called neutralization. Litmus goes blue in the presence of base. Obviously it's not going to go red. That happens with acids. That's just the way it is. Bases feel slippery. Just quickly, this is an interesting fact. An example of a compound that's a base is sodium hydroxide, and you buy that in the shops as drain cleaner. And it feels slippery because the sodium hydroxide actually breaks down the fats in your skin and turns them into soap. And so what you're feeling is the actual soapy hue being produced by the action of those bases. Okay, that's it for this particular mini lecture. I'll see you for the next one.